Right, so this is a third video of probability basics. So continue on where we left off. We defined the basic concept of probability, in which there are n possibilities, and if s of them are considered successes, then the probability of a success is just s divided by n. And then we went through the example of drawing the example was the probability of drawing 4 aces from a deck of cards. So what is the probability of failure? So if there are s objects or s possible successes, then there must be there must be n minus s failure possibilities. So the probability of failure is n minus s divided by n, and that's equal to 1 minus the probability of success. Okay? So let's go through this. So we have p, little p is the probability of success. So probability of success is little p. The probability of failure is 1 minus p. Okay. So if we know that, what is the probability of getting n successive failures? Okay, so we can think of that. Let's go ahead and, okay, so let's think about that. So the first failure gives us a probability of 1 minus p. Okay, so of that probability, the second failure has a probability of 1 minus p as well. And of those failures, we keep multiplying by 1 minus p, and we get 1 minus p raised to the n power. Okay, so that's the probability of getting n successive failures. So now, what is the probability of getting n failures followed by 1 success? Okay, well, we can just follow the reasoning that we've built. So we can write the probability, big P for the final outcome, the probability of getting n failures followed by 1 success is 1 minus little p to the n. And of those trials, the last one is a success. Okay, little p. So in general, let's generalize this a bit to our successes out of okay, sorry about that. Let me collect my thoughts here. So So the probability 5, the probability of getting n minus r failures followed by r successes. So in the above example, r was 1, and so the more general case is if we have r successes, and we can write the probability of that final outcome as 1 minus p to the n minus r times p to the r. Okay, and I'm noticing a mistake. So we want to get n minus, so in our first example, let's look at example 4. The probability of getting n minus 1 failures followed by a single success should be n minus 1. Okay. Right. Let me write that out. 1 minus p to n minus 1. Because we're interested in n trials, and if the first n minus 1 are failures and we get 1 success, then this is the probability of that situation. Okay, went back and fixed that. So now we're able to generalize it for a total of n tries. So this is n tries, as was that. The probability of getting n minus 1 failures followed by r successes is described as that. Okay, but let's say we're interested in all possible ways of getting r successes. Okay, we've shown this is really only one configuration of r successes, right? They happened at the very end of our n tries. Okay, but we could get a single success followed by a bunch of failures followed by the rest of our successes. So there are different ways of getting r successes. So what is the probability of getting r successes, period? Well, let's see. Let's consider that. So the number of ways of getting r out of n successes is simply n over the our binomial coefficient, right? That was the number of ways of getting r successes out of n tries. So back to our equation. So we have a probability of one of those configurations, but there's n over r possible ways of doing this. So the full probability of getting r successes is n over r times 1 minus little p to the n minus r little p to the r. And so what we've just described is the probability of getting r successes out of n tries in any order. this happens to be the binomial probability distribution. And Davis goes through some applications. We're not going to go through it now, but we're going to talk about probability distributions in the next couple weeks. So just like to point that out, and we'll cover probability distributions later. Okay, so the binomial distribution is relevant when little p does not change with each successive trial. Okay, we've assumed that little p here is constant with successive trials, and that is relevant. Okay, let me write this down here. So that's true for toss of different coins, for example, or for example, sampling from a very large sample size. Right, so if we have if we're sampling different objects, each successive sampling doesn't change what's left in the population because the population is so large. So this is where the binomial distribution matters.